Okay, in this video I would like to go through a problem in the ACT textbook, and hopefully we'll learn how to solve it. The problem goes like this. I'll take a notebook and show it to you on paper. Okay, we have x is a random variable uniformly distributed between 0 and 1, and then we have y is equal to x negative k. I'll show you in the video how it looks in the book. X is uniformly distributed between 0 and 1. Y is a function of x. It's x to the negative k. So we'd like to know what's the expected value of y. So how do we do that? Very interesting that we can do this a few ways. That's the beauty of... Well, first I want to do it the easiest, and then I want to do it a hard way. First of all, let's assume k is a number less than 1, because that's how it works. So let's imagine k is 0.8. Just using, I like to use a number, let's use 0.8. So it's x to the negative 0.8. You see here, x to the negative 0.8. That's what y is. Now there's an interesting rule that to find an expected value of a function, there's an extremely shortcut. It's actually easier to find the expected value of a function of a random variable than to find the actual distribution of that function. So it seems complicated, but it's actually easier. In other words, if I tell you x is a certain random variable, whatever it is, let's say here it's uniformly distributed between 0 and 1, and then somebody goes along and says, okay, I have another one, a random variable that's a function of x, let's say y is equal to x squared or x cubed. So normally there's a complicated how to figure out the PDF or the CDF of y. There's all kinds of tricks and things that's quite confusing. We'll see soon how to do that. But here goes somebody tries to make it even more confusing. He asks you what is the expected value of this function, of this new function. So it seems like he's really, you could do it you first find the PDF, and then you multiply it by x, and then you go through all the values, you find integrated. It can take you a long time, and it can be just messy. Here, do something very, very clean. You just take this function that's x negative 8, you multiply it by fx. Fx in this case is the 1. It's nothing, because fx is just the PDF of the original function, so it's 1. And you just do it from 0 to 1, integrate it from 0 to 1, just like any expected value. So I'll show you how you do that. Take a look what I wrote here. It's 1 to 0, x to the negative 0.8 dx. And we all know that simply the rule is you just go up 1, so it gets negative 0.8 gets 0.2 divided by, you just take whatever you got upstairs, just take downstairs, and you go from 1 to 0, and I'll just show you the work in a second. So it's 1 divided by 0.2, that's equal to 5. show you the work here. You should be able to follow along. Look what you got here. You got first the integration, then you see that turns into x 0.2 over 0.2. You do it from 1 to 0. Then you got 1 divided by 0.2 equal to 5. So the expected value is 5. Just looks too good to be true, but that's the answer. In other words, basically we have here, just to tell you an idea what's happening here, we're taking this thing that's uniformly distributed between 0 and 1, we're taking and we're doing x to the negative 0.8. So actually this can be any number between 1 and infinite. Why? Because if it's 1 to the negative 0.8 is 1. But as you go lower, let's say you get half to the negative 0.8 or a quarter to the negative 0.8 and so on, the lower you get, let's take an example. Let's say you want to have x is a quarter to the negative 0.8. So that's a quarter to the 0.8, 1. Take a look at the bottom of the page. You see 1 over a quarter to the 0.8. So that's actually, if you realize, it's telling us it's getting a tiny number, because a quarter to the 0.8 is actually a number that obviously is less than 1, and so on. The more you go, the x gets smaller. Let's say x gets at 100th. 100th to the 0.8 will be a small number. So it definitely, you realize that the smaller x gets, if you make that a function of x, y is equal to x to the negative 0.8, so the y gets larger and larger. So it's definitely a graph that extends from 1 to infinite, but somehow it has an expected value that's finite. It's not going to work if k is more than 1. I'm not going to prove that here. You just do it for yourself. You must put in k as a value less than 1, and then it's very easy to find. And as you realize, it's always going to be 1 over the one that's missing from 1 to k. So if you started with 0.8, you just 1 over 0.2, and that's, so you can make it like 1 over 1 minus k. That's very, very simple. That's the fast way how to do it.